Hey, geometry friends. Yes, we're still in chapter 6, but we're going to talk about something you think you know about, and you do know about it, but we're going to talk about it in a different way. Today, in section 6.4, we'll talk about rectangles. So, what is a rectangle according to our geometric definition? Well, you know what it looks like. You've been drawing them since you were a kid. Rectangle! However, we're going to say a rectangle is more than just this four-sided figure that looks kind of like this. It is indeed a parallelogram. Rectangle is a parallelogram with a right angle, right? Like, think about it. So you got the parallelogram, opposite sides are parallel, blah blah blah, and then we know opposite sides are congruent and all that stuff. But then you throw a right angle in here, and then all kinds of dope things start happening. So if this is a right angle, then you know this one has to be right. And if these two are right, then you know these are supplementary. That means this one has to be right. And what? Look at that. So a parallelogram is a rectangle with one right angle. Well, then it means all four right angles. So basically, a rectangle is a parallelogram with four right angles. Before we get down to the first example here, we're going to talk about this theorem around rectangles. And basically, it says if we have a rectangle, then which is a parallelogram. So if you've got this parallelogram, which is a rectangle, then the diagonals are going to be congruent. So more than just bisecting each other like they do in a regular parallelogram, the diagonals are congruent, which is kind of fun and beautiful and awesome and so forth and so on. Okay, so here is our first example. We're going to use properties of rectangles. So a rectangular park has two walking paths as shown, they're diagonals. And if PS is 180 meters and PR is 200 meters, PR is 200, find QT. So PS is 180, let me write that down. And PR is 200. Find QT. Well, the fact that these are diagonals, I would say QT is 100 already. I don't know what your text wants us to do, so I'm going to kind of think within the box of the text. I could look at what they did, but I'm going to just talk about us. I'm looking at this part right here, right? So this is S, R, and this is P. And you know that this is a right triangle. And we've talked about this, which is the Pythagorean theorem, which tells us stuff about right triangles. A squared plus B squared equals C squared. So we could find SR and do some other fancy stuff and see if, well, I know if this is 180, this has to be 180. And whatever this length is, I can then do Pythagorean theorem and figure out that this is half. But I don't think we're doing that. That seems like a whole lot of stuff to go through. So I'm going to stop here and I'm going to say if PQ, if PR rather, if P, now I'm going to try to write R. If PR is a diagonal of a rectangle, then QS has to be equal in length. And if PR is 200, then QS is 200. And if QS and PR are diagonals of a parallelogram, then they bisect each other. Therefore, QT is equal to TS, and we know that QT plus TS, I know I'm going far, guys, is equal to 200 because it's equal to QS, right? QT plus TS is 200 because that's what, right. And we know that they're equal. We could do substitution, and basically we get that QT is equal to 100. I'm going to stop there. So, like I said, QT is equal to 100. So we've arrived to example 2, and here we're still using properties of a rectangle. We're given some information here. So let's see. We're told that angle KJL, I'm going to mark it in red here and mark it in red here, has this measurement, and this other angle, it is JLK, that's JLK, this one here, JLK right here is has this measurement here. We're supposed to find X. What I know about these two angles, guys, this angle here and this angle here, is that there are two other angles a part of a right triangle, right? So I know that this is the a rectangle. A rectangle can, if you draw a diagonal, you make two right triangles. You've got this little right triangle here. And what I know is that if this triangle has a 90-degree angle, then the sum of these two angles is 90 degrees as well. So that gives me a beautiful equation. So here's our gorgeous, okay, so here's our gorgeous equation. And we can replace each of these with the measurement of the angle. And we get this even better, more useful equation. I don't know why I can't write today, babies. Is equal to 5. Plus 5 is equal to 90. And we're going to do our old algebra deal. Joining like terms together, plus 9 equals 90. Subtract 9 on both sides. You guys know where this is going. 9x is equal to 81. X is equal to 9. So in case you didn't know enough about the diagonals of a rectangle, we've got a theorem about them. Oh yeah. If the diagonals of some parallelogram, so you're walking down the street, you're checking out this parallelogram, you're like, dag, your diagonals are congruent. What you get to know now about that parallelogram is that it's a rectangle, right? So here's another way to figure out if you've got a rectangle, not just if you have a right angle, but if you can look at the diagonals of a parallelogram and you determine that those diagonals are congruent to one another, then you know you have a rectangle. The more you know. So this brings us to example 4, rectangles and coordinate geometry. So here we've got this quadrilateral. They're giving us that much information. And we're told that this quadrilateral, we need to determine that this quadrilateral, whether this quadrilateral is a rectangle by using the distance formula. So that's not a whole lot of information. So what do we know? We know if we have a quadrilateral such that its opposite, one pair of opposite sides are both the same in length and parallel, we can say that that thing is a parallelogram, right? And then we know that if we can prove that the diagonals, I'll draw them in orange here, that the diagonals are equivalent. So if we, the theorem goes that if we have a parallelogram, right, then we can prove that that parallelogram is a rectangle by virtue of the fact that the diagonals are equivalent. So I know how to go from a parallelogram, which is the shape I'm drawing here, to a rectangle, which is this guy here with its little 90-degree angle. I know how to prove that. The thing I need to do is prove that I have some old quadrilateral here, some four-sided figure, and prove that it's a quadrilateral. So for me, I'm looking at this as a two-step situation. One, I've got to prove that the quadrilateral is a parallelogram, and then I've got to prove that the parallelogram is a rectangle. And they asked us to use the distance formula. So if I'm only able to use the distance formula, then what I have to do is prove that PS is congruent to QR, and then PQ is congruent to SR. If I can prove that, then I know I've got a parallelogram. So that brings me to the first step. Then if I can prove that PR and SR are congruent, then that brings me from this second step to this third step, knowing that I have a rectangle, right? Just a little caveat, I would prefer to go find PS and QS and make sure that they're QR and make sure that they're congruent, and then prove that they're parallel by doing like the slope, change in Y over change in X, making sure that the slopes are the same. And if you got the same slope, you've got the same parallel, and then we can do that. But it's easier, but we're going to honor what the textbook asks us to do. And so let's go through the work. So part 1 is to proving that PQRS is a parallelogram. And so we're going to first check out PS and QR in terms of its length, and then PQ and SR, PS and QR and PQ and SR. So let's see what we get. Using the distance formula, which we know is written like this, the difference in X is quantity squared plus the difference in Y is quantity squared square root. So when we apply that formula right here, get rid of that there, get it out of the way. When we apply that formula right there, we get -5 minus a -7, which is a +2. Quantity squared, we get 4. And this is 3 quantity squared. We get 9. So we end up with the square root of 13 here. So this becomes a 4, this becomes 9, and we get the square root of 13. Let's see what happens with QR. we have for QR 1 minus a minus 1 quantity squared, which is 2 squared, which is 4. 1 minus a minus 1 is 2. 2 squared is 4. Plus negative 1 minus a minus 4. 1 minus a minus 4 is negative 1 minus a minus 4, rather, is negative 1 plus 4. Negative 1 plus 4 is 3. 3 squared is 9. You see what's happening here, right? We get 2 squared 4 plus 3 squared 9 is 13, the square root of 13. So we see already that PS and QR are indeed congruent. Let's see what we can do for PQ and SR. So here we are comparing PQ and SR, and we see that we get, once we plug everything into the distance formula, we get a negative 5 minus 1, which is a negative 6, quantity squared 36. And then we get 3 minus a minus 4, minus 1, which is a 4, quantity squared, we get 16. So we have 36 plus 16, which gives us 52 underneath the radical, or the square root of 52. Let's see what happens here. So we have negative 7 plus, because minus minus gives me a plus 1. Negative 7 plus 1 is a negative 6. Negative 6 squared is 36. So that's going to be 36 here. And then negative 4 minus 0 is really just negative 4. And when I square negative 4, I get a positive 16. Same thing we got underneath the radical up here. So what that tells me is that I'm going to have 36 plus 16, which is going to give me the square root of 52. So indeed, the first part that I have to prove is done. Yes, indeed, this is a parallelogram. Let's go to the next part. Now this part is kind of straightforward, I guess. Part 2 is really just proving that so we're proving that that the parallelogram is that PQRS, now we're getting to the meat of it, PQRS is a rectangle, all right? And so we're going to do that because we already know that PQRS is a parallelogram. Let me get a little bit more space. We're going to do that by proving that the diagonals are congruent. So I want to prove that PR is congruent to SQ. And so again, we'll pull out our distance formula. So we've set up the distance formula with figuring out the length of PQ and SQ. And so we'll calculate. We get negative 5 plus, right? 1 is going to be negative 4. Negative 4 quantity squared is 16. So I have 16 underneath the radical. And to that, I'm going to add 3 minus a minus 4 is going to be a positive 7. 7 squared is 49. So I've got 16 plus 49, which is equal to the square root of, let's throw one over there, 65. I believe I have. Let me see if I can get it there. Square root of 65. All right, over here, negative 7 minus 1 is going to be a negative 8. Negative 8 quantity squared is 64. Plus, and this is all underneath the radical, 0 minus a minus 1 is plus 1. Positive 1 squared is just 1. And notice, guys, I get the I get the square root of 65. Let me try to make that look pretty. I didn't mess up, I promise. So I get the square root of 65 for both of these. Let me write it over here. Square root of 65 and the square root of 65. And so now we can safely say PQRS is a rectangle. I know you guys were like waiting on bated breath. This was the most awesome proof ever. Okay, it was all right. Well, it wasn't really a proof, right? It was more a analytical geometry, what do we call it? Coordinate geometry discussion. So now that we've done that, we have done enough examples for you to work on section 6.4. Let me know if you have any questions about the material. I could re-explain. We could talk about it later. We can do what we need to do. Guess what? I look forward to seeing you, and I hope you take good care. Bye-bye.